Hi, in this video we are going to talk about the concrete implementation of the Dijkstra shortest path algorithm. So let's get started. I'm going to create a distinct package with the name, for example, Dijkstra algorithm. I'm going to create a new class with the name edge, another class for representing the vertices in the graph. Of course, we will have the algorithm itself, and we are going to have an application.java from which we are going to test our application. So, in the edge is basically quite easy. We just have to store double weight. It's going to represent the weight of the edge. And basically we will have a vertex with the name start vertex, and the private vertex, the target vertex. Basically every edge connects two vertices, the starting vertex and the target vertex. I'm going to give these names, feel free to rename it as you wish. And I'm going to generate a constructor, so source, generate constructor for the weight, start vertex and the target vertex. I'm going to get rid of the super, add some spacing, and I'm going to generate some getters and setters. So generate getters and setters for the start vertex, target vertex and the weight. And maybe we could implement the edge that we get rid of this start vertex, because basically the edge is pointing to the target vertex, but whatever, I think it is a bit better solution to store a vertex representing the starting vertex and another vertex, the target vertex. Okay, the vertex basically will have a private string name. Then of course we have to store the edges, basically the adjacencies list. So far we denoted the adjacencies with a list of vertices. Basically we should name it adjacencies edge list or whatsoever, but just for demonstration purposes I think it's going to be clear that of course we have a single vertex, and a vertex can have as many neighbors as the number of edges, because every edge is pointing to a neighbor or an adjacent vertex, whatever we call it. So basically that's why I store a list of edges. Of course we have to track whether we have already visited that given node or not, so we will have a boolean visited. We have to track the predecessor, so the vertex, previous vertex or predecessor. It's crucial when we want to construct the shortest path tree. We have to update the minimum distances as well as the predecessors in order to be able to track that from what vertex we came here, which is the shortest path, of course, as we have discussed in the theoretical section. And of course we will have the minimum distance, so we have to track that what's the minimum distance from the starting vertex to the given vertex we are standing on. So for example it will have the minimum distance name, and I initialize it to be double that maximum value. That's what we have been discussing, that in the first iteration of the algorithm we iterate through all the vertices and we initialize it to be infinitely far from the starting vertex, because we don't know the distances from the starting vertex in advance. So that's why double that max value is approximately infinity. Okay, what's very important that I'm going to have, of course, a constructor. In the constructor I'm going to get a name, and okay, this dot name is equal to the name, and of course we have to initialize the adjacencies list in order to avoid null pointer exception. Okay, then I'm going to have a, for example, public void add neighbor. It's going to be an edge this time. So this dot adjacencies list dot add, we have to add this edge. Okay, I'm going to override the toString method, and I'm going to return the name. So return this dot name, so the name of the vertex. Anyways, I'm going to generate the getters and setters for all of the field variables. So the adjacencies list, min distance, name, predecessor and visit. And one more important thing, that we are going to create a priority queue where we store the vertices. This priority queue basically is a heap. As you may recall the theoretical section, we have to get the neighbor vertex with the minimum distance. So for example, we have a neighbor with edge weight 7, another neighbor with edge weight 1, and another neighbor with edge weight 5. Then we have to go to the vertex that's the nearest, and basically the nearest where the minimum distance is the smallest. So basically we have to implement a comparable interface, and we have to tell Java that, okay, we would like to compare vertices. We would like to compare vertices according to the name, so we would like to sort vertices in alphabetical order? Of course not. We would like to sort the vertices as far as the number of edges are concerned? Of course not. We would like to sort basically the edges according to the minimal distance, because on every iteration we would like to consider the vertex with the minimum distance. Okay, maybe it would be a better name, that distance. Okay, I'm going to rename it to distance because the minimum distance is a bit confusing, because it's not the minimum distance always. It is just the distance from the starting vertex. So I'm going to rename it to distance. And I think that I have to get distance and set distance, I have to rename it. And just to be consistent, I'm going to rename it as well, so the distance is going to be equal to distance. So we have to implement this comparable interface. We would like to compare vertices according to what? According to the distance. So I'm going to have the other vertex, for example, and I'm going to return the double.compare. The first is the distance, the second one is the other vertex dot get distance. Okay, so again, we have to create an edge class, and of course an edge has an attribute, the weight, basically the edge weight. And of course every edge has two vertices, the start vertex and the target vertex. So we are going to create a constructor and the getters and setters accordingly. The vertex is a bit more complicated. First we have to use the adjacencies list, and instead of vertices we are going to store edges in a list. Of course we have to track whether we have visited that given node. We need a predecessor in order to construct the shortest path tree, and we are going to track the shortest path according to the predecessors. We're going to backtrack basically. And the most important one is the distance. This distance represents the distance from the starting vertex. Every vertex in the graph has a distance from the starting vertex. Maybe it is the maximum value, whatever, but every single vertex has a distinct distance. And that's why we have to implement the comparable interface, because we are going to use a priority queue, and we have to tell Java and the priority queue that, okay, we would like to compare vertices, but according to what we would like to compare them? Of course, we would like to compare them according to the distance. And that's why we have to override this compare to method, and this double.compare is going to compare that what's the smaller one, the distance or the other vertex.get distance, and it's going to return +1, -1 or 0. As you can see, the value 0 if d1 is numerically equal to d2, which means that the distance is equal to the other vertex.get distance. It's going to return -1 if the distance is smaller than the other vertex.get distance, and anyways it's going to return +1. So basically this compare to method is going to decide for Java that, okay, we would like to sort basically these vertices, we would like to compare two custom objects, and okay, we have to specify that according to what feature we would like to make this comparison. Okay, so in the next video we are going to implement the algorithm itself. Thanks for watching.